So I'm not going to be talking about string theory today, I'm afraid. Though if they'll have me back, I might come and talk about string theory another time. But I want to talk about something which has been a passion of mine for a few years, essentially because it's a sort of manifestation of many areas of science that many of us learn at high school. It's not very difficult science, but it's something that is sort of at the heart of, for me, what science is about, which is understanding nature and understanding the beauty of nature. In particular, the phenomena that we can see around us every day if we only know to look. And I think that's the really important thing, that there are so many phenomena around us, but people just don't know where to look for these things. I should say at the beginning that a huge amount of the information that I learned about atmospheric optics comes from a website, www.atoptics.co.uk, run by actually a chemist in the UK called Les Cowley, who is really an expert on this and taught me a great deal about this subject as I was coming to learn about it 7 or 8 years ago. So there's a number of reasons that I would like to give a talk like this. I don't know if the writing is going to be clear there. I'll read it anyway. So the motivations that I want to give this talk, this first one really is that the phenomena that I'm going to talk about are all around us when we know to look. One of the things that I find fascinating is that when I see these things, and I see these phenomena very, very regularly, I point them out to people on the street and show them, and often they think that I'm mad. But when I explain what's going on, they're fascinated, and they've never seen them before. What's lovely then is that they'll then come back to me and say, I saw this again, a week later, 2 weeks later. Okay, so once you've seen it once, it's all around you. Sometimes I have good experiences telling people this. Sometimes people just think I'm mad and then walk off. So I'd like to clear my name a little bit for when you see me staring at the sun. I'm not actually staring at the sun, but I'm looking at the phenomena which are caused by the interaction of light and water and air. So we've got a quote here by Paul Dirac, the famous British physicist, who said, "I consider that I understand an equation when I can predict the properties of its solutions without actually solving it." And the reason that I've got this there is that as a string theorist, as somebody working within the realm of theoretical physics, it's very difficult often for this to come true, for us to have an equation where we can understand it so perfectly that we can just imagine what the solutions are going to be. The equations for string theory, though they're quite compact to written down, are so manifestly complex in their solutions that it's very difficult to get a real intuition as to what's going on. But the topic of atmospheric optics, the science is really very basic. Okay? So a lot of it, once you understand the basic science, you can see precisely what's going on. And I think that's a really beautiful aspect of this topic. So it's a mixture of science and experience, and that experience is really knowing when the conditions are right for a particular phenomenon to be around, and understanding the science to know the way light is going to interact with water in particular states. And the science is actually of very simple ingredients, that of light and air and water. There are still some mysteries here. There are still some things that we actually don't understand, even though these ingredients are very simple. But the constituents are very simple, and we can understand a great deal of what's happening. So this picture here I'm actually going to explain later in the second part of the talk. So the first part of the talk that I want to talk about is about halos. Okay? Halos and different ice effects. So halos are caused by the interaction of light from the sun or the moon on ice crystals in the sky. And those ice crystals cause the light which passes through them to be refracted and reflected in different ways to cause spectacular effects. So these effects, you might imagine that if you've got ice in the sky in some random combination, it's just going to give you a random sort of pattern and a random array of light in the sky. But in fact, the way crystals of ice form on Earth in the atmosphere are such that actually what you get are very, very specific patterns, and I'll talk about those patterns in a bit. What's lovely is that the right conditions for having these ice crystals are frequently all around us. And you might imagine that you have to be somewhere very cold for this to happen. But of course, up in the atmosphere, relatively high up in the atmosphere, the conditions are already cold enough for ice to form even in the summer. So these effects you'll actually see quite often, especially when the weather is changing around here. If it's about to move from a dry period to a wet period, you'll often find halos around this area. I've seen them a few times around Musenberg. In particular, look out for cirrus clouds. I'll show you a picture of these in a moment. So cirrus clouds are clouds with a high density of ice crystals, and it's these particular ice crystals which cause these wonderful displays. So you might imagine that the phase diagram of water is relatively simple. So here we have a graph, we have temperature here, and we have pressure up in that direction. And when you take water and you put it under particular conditions, you put it at a particular pressure and a particular temperature, well, you'll either be in the gaseous phase or the liquid phase or the solid phase. And of course, there are certain interesting points here. But in fact, it turns out that the phase diagram of water is rather more complicated than that. So if we look at the full phase diagram of water, in fact, it looks something like this. So you do have the gaseous phase and the liquid phase, but in fact the solid phase is rather complicated. And the reason for that is because under different conditions, the crystalline structure of ice is very different. So sometimes you'll get hexagonal crystals, sometimes you'll get many, many different patterns. It turns out that on Earth, at atmospheric pressure or around atmospheric pressure, what we actually have is this so-called ice 1H. And we know that all snowflakes are different, but it turns out that the symmetry properties of crystals of ice, or the structure are actually all the same, or relatively similar. And that is to say that what we find is that ice 1H, this ice formed on Earth, is in general a hexagonal crystal. And that may take different forms, so you may get these plate crystals, flat crystals, you might get column crystals, or somewhere in between, and even sometimes pyramidal crystals. But the fact that there's this very, very set structure of a hexagonal pattern, a six-sided pattern of the crystals, is what gives rise to the particular pattern, the particular halos that we get on Earth. I'll show you later what happens, or what we expect to happen on different planets where we don't have water in the atmosphere, but ammonia or carbon dioxide forming crystals, which cause different types of crystals, so they won't necessarily be hexagonal, and they will give rise to different halos again. So in the background, we see these cirrus clouds. I'll show you a more detailed picture in a moment. And what we have is essentially, it's not very clear, you'll see a clearer picture in a moment, but we have light passing through a hexagonal crystal, and as it passes through the face of the crystal, as it moves from one medium to another, the light refracts. And by the refraction, what that means is that light is bent, and in particular, the different wavelengths of a light get bent by different amounts. Okay? This is refraction. So in the background here you see so this sort of wispy cloud are the cirrus clouds, and these are the sorts of clouds which you'll very, very often see halos when these are around. Okay, so imagine for a moment we've got the sun, and we have light coming from the sun, and we have a single crystal there. And the single crystal is a particular orientation, and as a beam of light passes through it, it splits, and that beam of light is then sent, the different colors are sent in different directions. Okay? So this is the refraction of the light through a single crystal in the sky. So you can imagine a few crystals in the same place, but taking different orientations, and those different orientations are going to give rise to light going in different directions. Now a person here is therefore going to see some colors coming from that particular crystal, but the person here is not. Okay? But of course the sky isn't just full of crystals at that one point taking all different orientations. The sky is full of crystals all over in the cirrus clouds. Okay? And from an individual position, from a position here, this person will see light coming from that direction refracted through that crystal, and they will see light coming from a position up here refracted through that crystal. And in fact, what they'll see is essentially a circle around the sun. This person will also see the same thing. And the effect is this. So this is a 22-degree solar halo. The reason it's 22 degrees is because the angle of refraction, the amount that the light is bent as it passes through, as it passes in and out of the crystal, is 22 degrees. So if you point towards the sun and you point towards the circle, you'll find that it subtends an angle of 22 degrees. Okay. So this was actually the first halo that I ever saw. This was in Spain, in Santiago de Compostela, and I'd read about them many times before. And one day I looked up, I was wearing sunglasses, which makes it easier to see them. I looked up and there was this perfect circle in the sky around the sun. And the lamppost there is just there so that it was easier to take a photo. So in general, just put yourself in a position where you're not going to be blinded by the sun, or put your hand there, so just don't stare at the sun, whatever you do. But put yourself in a position where the sun is blocked out and you'll be able to see this perfect halo around the sun. What I found amazing was that the first time I saw this, which was probably 7 or 8 years ago now, after that I saw it every single week. Okay, for months and months and months I would see them. And I would speak to people about them and they had never seen them. And then I would point them out to friends and colleagues. Every time I saw them I would rush everybody out of the physics department to come and see. And once they started seeing them, they saw them all the time. Okay, so if you've never seen something like this, just keep an eye out from now on. You are likely to see this very, very regularly. So what's happening here? Let's understand that again. So we have ice crystals of different orientation. In this case, these are column crystals because the column crystals can orient themselves quite nicely in all different directions. By column crystals, I just mean long, thin crystals with the hexagonal structure on the cross-section. And these hexagonal crystals take all different orientations, and you can work out which bit of the halo is coming from a crystal of which different orientation. In fact, the light isn't always bent by 22 degrees, but it turns out that the highest intensity of light, or the highest amplitude, does come from the 22-degree direction. So in fact, it's bent by up to about 36 degrees, but at 22 degrees, that's where most of the light is bent, depending on the precise orientation of the crystal. So when I tell people about this, they often say that they've seen a similar effect around the moon, which may be true because there are indeed lunar halos, but very often what they're talking about actually is a lunar corona. And a corona is different. A corona is caused by droplets of water, so not ice crystals, but droplets of water, and it's a diffraction effect of the wave-like nature of light as it goes past the droplets of water. I'll talk about this a little bit later, about these corona effects and the cloud iridescence, where you see them as well. But this is a different effect from the solar halo. So again, you see the 22 degrees is from the angle subtended towards the sun and the halo itself. And what you also see is that there's a slightly darker region inside. Again, that's because the 22 degrees is actually, while it's the direction where there's the highest amplitude, it's also roughly the minimum direction where the light can be refracted through. And outside, it can be refracted to higher angles, up to 36 degrees. So in fact, you get a darker region inside the halo than outside the halo. Sometimes you won't get the full halo, you'll just get a little bit of it, and that's dependent on the particular orientations of the crystals. So sometimes the crystals, depending on the wind and the humidity and the various conditions, the crystals themselves will not align around all different conditions. So you'll just get the top and the bottom of the halo, or you'll just get the sides, or you'll get the whole thing, depending on what the different orientations of those crystals take in the sky. This was a photo. This is a lunar halo. So this is really a halo rather than a corona, again in cirrus clouds, taken in Mozambique. So this must have been about seven years ago as well. This will be a familiar building to many. So this was about a year ago. So I see these, I work up at UCT, and I see halos very, very often above the mountain. And again, try and point them out to people as they come past. This isn't my photo, but this was taken in the South Pole by probably the foremost halo photographer in the world. We'll see some more of his work later, a guy called Marko Rikkonen, a Finnish photographer and atmospheric scientist. So in the South Pole, in general, it's not from cirrus clouds, but what's called diamond dust. And diamond dust is simply snow and ice picked up by the wind, sent into the sky, and these, again, cause the refraction of the light through the crystals in the sky. So the South Pole is really one of the foremost places to see it. So the next thing I want to talk about is exactly the same effect, but just coming from a slightly different crystal type. This time, rather than having column crystals, we have plate crystals. And plate crystals, which are much flatter, tend to lie horizontally in the sky. And what that means is that rather than taking on all different orientations, we don't get the full halo, but all we get are the two side parts of the halo. Okay? Because they lie horizontally, the light passing through them passes through horizontally. Okay? So what you have here, you have halos to the right and plate crystals to the right and the left, and as the light passes through, what you see are these so-called sundogs. Sundogs are really the sort of highlighted points at the side to the right and the left of the halo.
What will cause them to be horizontal?
So the way the air resistance, or they lie in the air, they actually like to lie horizontally. Yeah, exactly, that's right. So this is a sundog, so this is my hand blocking the sun out. This is a sundog here just to the right. There are some other effects going on here as well. So here you see a sundog. So here you can't actually see the rest of the halo, and this is because this is predominantly made up of these horizontal plate crystals. Here again, these are very, very bright sundogs that you see here again in cirrus cloud. So sundogs can be incredibly bright. Is there a question there?
Where's the name come from?
Sorry?
Where's the name come
Sundogs. I think it's just the idea of sort of the sun having two dogs by its side, the sort of accompanying the sun. It's a good question. I've never pinned down exactly where the name comes from, but I always imagine it as two dogs accompanying the sun. That's as best as I've got. So sometimes if you zoom in on a sundog, so this is a photograph here of a piece of cirrus cloud just passing through the region where the sundog is visible, and you get these wonderful iridescent effects. Again, it's not limited to the sun. These are moondogs. Again, not photographed by me. This is photographed by David Cartier in Canada. You've got these beautiful moondogs here, but you also have another phenomenon here, again from plate crystals. So what you have here, these are the plate crystals, but rather than the light passing through and refracting, what you have is the plate crystals acting like a mirror. So the light from the sun bounces off them, so you've got plate crystals all down here, and these are the regions where you see the reflection, not refraction, reflection of the light off the plate crystals floating again in the region below the sun there, or the moon in this case. So I've shown you a picture of what happens when you have column crystals, and I've shown you what happens when you have these plate crystals. But sometimes the conditions are right such that you'll have a distribution of lots of different types of crystal, and then we'll get something like this. So here we have a little part of the halo, the 22-degree halo, going up around here. We've got a sundog here. We've got what's called an upper tangent arc at the top. I'll zoom in onto some of these bits. So here we have the sundog and the 22-degree halo, but in particular, if you zoom in on this region of the photograph, so I took hundreds and hundreds of photos these days, and if you zoom in on this, what you see are these very, very subtle effects. These are all Lowitz arcs, and these Lowitz arcs are actually caused by a very specific orientation of the crystal. So the crystals like to lie with two of their points lying horizontally, and the crystals are oriented around these points. And it turns out that the orientation of the crystal as it rotates through here gives rise to these 1, 2, 3 Lowitz arcs, the upper, lower, and middle Lowitz arcs. And actually this photo that I took, this was in Portugal about 7 or 8 years ago, this was one of the first photos ever taken, in fact, of the full set of Lowitz arcs. People have taken more since then, but this was quite an important photo. You can do simulations of this. Of course, if you know what sort of crystals are in the sky, you can do a simulation and work out the path of light through the different crystals. And this is actually a simulation here of the upper, lower, and middle Lowitz arcs for the particular time of day and the distribution of crystals in the sky and the height of the sun in this particular day. So you can compare there just about between the photo, enhanced photo, and the simulation there. So we also have the so-called perihelic circle, a circle which you take the sun, and it's a circle which goes all the way around the sun, all the way around the viewer, lying horizontally. And these again come from these plate crystals lying horizontally as the light bounces off various faces. So in fact, this whole arc going all the way around isn't just made up of one type of reflection and refraction of the crystals. What's important, though, is that it always comes in and out of parallel sides of the crystal, and because of that, the refraction which happens, the splitting of the light which happens as the light passes through one face, is undone as it comes out of the other face. And so, in fact, this circle around the Earth or around the sky is entirely white. In fact, there's a very, very specific point you can see up there pointed. It's a slightly brighter point, is the 120-degree perihelion, is a very specific spot where light is passing through in a particular orientation. So you get this circle, you've got the sun, and then at 120 degrees either side, you've got these other brighter points of light. So this is not taken by me, this was a photo taken in Israel, but here you see this is taken directly up. So here you have the top of the 22-degree halo, and then all around the sky you have this perfect circle. And here you can just about see, so in fact we've got the sundogs here, and I guess around here you've got the 120-degree perihelic circle. We've also got these upper tangent arcs. So the upper tangent arc is again from a particular orientation of the crystals, this time column crystals. As the light passes through in a very, very specific orientation, you get arcs on top of the 22-degree halo. Here you have upper tangent arc, and here you can also have a lower tangent arc. This again isn't taken by me. This was again taken in Alaska. So you can have different halos. This is a simulation here, but you can have you can simulate what would happen with different types of crystal. And here we have a pyramidal crystal, and the pyramidal crystal can give rise to all sorts of different patterns. So we do see halos coming from pyramidal crystals occasionally, but they're a lot rarer. And if you're incredibly lucky and you're in the South Pole, I'm aware you probably can't read this, but I'll read through some of it. If you're in the South Pole and you're incredibly lucky and there's a particular distribution of ice in the sky, you'll see not just a 22-degree halo and some sundogs, but you'll see an entire distribution of many, many different halos. So here, this is the sort of world record. This is the largest halo display ever seen. Again, it was photographed by Marko Rikkonen, and it was 24 distinct halo types, which means 24 different types of orientation and crystal types, ranging from 22-degree halos, 46-degree halos, superlateral arcs, perhelix circles, all the way down to lower tape arcs and Greenlander's anthelic arcs and all sorts of interesting names. So just imagine coming out of your accommodation in the South Pole, looking up into the sky and seeing something like this. So it's really absolutely spectacular. So we have here, again, this is just blocking out the sun. So here we have the 22-degree halo, we have sundogs, we have a perhelix circle, we have the upper tangent arc, we have a 46-degree halo, and then many, many others beside. This one in the middle is the so-called circumzenithal arc, which I'll talk about in a moment. And then if you look straight up, you can see the perhelix circle, and at the point opposite the sun in the sky at the same level, you see this point where various arcs come together and cross over at this anti-solar point there. Again, each of these arcs comes from a very, very specific orientation of crystals in the sky. There's a rather lovely way of describing this, the so-called circumzenithal arc. It says the first, I'll read it from here. The first sighting is always a surprise, an ethereal rainbow fled from its watery origins and wrapped improbably about the zenith. I rather like this description. It's also sometimes called a smile in the sky. It's just this perfect, very, very colourful, just because of the particular way the light refracts through it. It's a particularly colourful halo. These are really lovely to see. I've seen a couple of these in Cape Town before. And now just to show that this isn't camera trickery, well, the next one could be camera trickery, but I promise you it's not. Here's a video. This is both of there's a 22-degree halo. There's a lovely upper tangent arc. You can see here's the circumzenithal arc, which is incredibly bright and colourful. And then there's a perhelix circle also running all the way around the sky. So although it seems like I've been able to explain away everything that's happening there, this is still actually an ongoing science, and trying to understand exactly what's happening in particular situations for very rare circumstances is still not entirely known, and people still write papers on this. So if there's a particular halo display seen, people try to simulate precisely what's happening in terms of pyramidal crystals and different structures of crystal, which might give rise to precisely this pattern of halos. So while I haven't been to the South Pole, I was extremely lucky to see a particularly special halo back in 2008 in Paris. I was at the Louvre and I saw a little bit of a halo, and I thought, wouldn't it be amazing to see a halo, proper halo in Paris? And it disappeared, and I walked up to the Eiffel Tower, and of course, just as I got to the Eiffel Tower, I saw this, just a perfect halo around the top. And again, what was amazing for me was that I stood there and looked up, and there were hundreds and hundreds of people around also looking up, and nobody seemed to see this until I pointed it out to them. So it's amazing that people can look directly at something, but because they don't know to look for it, they don't know that these effects happen, they just don't see it. And so it's really lovely to be able to talk to people and to tell you to look out for these things, because they really are all around. This was another particularly nice display. So this was in Munich a few years ago. And what you see here, so you've got the sun here, you've got a sundog just to the right. I don't know how clear this is. And then you've got a reflection of the sun and a reflection of the sundog. So these are 4 different images of the sun, all through refractions and reflections. And this here is a zoom of this sundog here. So these are so-called sky pools. So sky pools are a reflection of the sky on water, on non-flat water, and you see these wonderful whirls. And it's the reflection of the sundog in the sky pools in this lake in Munich. again, another photo from Munich here. You have a 46-degree halo, you've got the 22-degree halo, the Sundogs, and the upper tangent arc. So again, these things are really all around if you know to look.
Excuse me.
Yeah.
You're describing as if there's one crystal involved or in a particular angle, but obviously there's millions of crystals.
Absolutely. So the whole thing is a cumulative effect from many, many crystals, taking all different orientations. Yeah.
So how does that light come out in one direction? Are you talking about the 22-degree angle, but it's certainly coming in, hitting another crystal in front of it?
Absolutely. That's a very good question. So so there's two things. First of all, the light which reaches you generally passes just through one crystal. So you can work out the distributions of crystals, and in general, the probability of light from the sun passing through a single crystal is very low, and therefore passing through two is extremely low. So this comes from passing through a single crystal. Of course, at the same position, there'll be another crystal with different orientation, or at a similar position. The point is that the light from there won't reach you because it's at the wrong orientation. It'll reach somebody else who's also looking up. So yeah, the sky is full of different orientations of crystals, and it's only those which are in exactly the right orientation to reach you which will send the light directly to you. Does that answer the question? Yeah. So again, you can do computer simulations and you can work out exactly what sort of crystals are going to give rise to exactly what parts of the display. But what's rather nice about that is that you can then work out what would happen on Jupiter and Saturn, or indeed on Mars. And I gave this talk in Paris a couple of years ago, and there's actually a team there who is analyzing the Mars rover photos, and they said that they're now going to start going through and seeing if they can find any Martian halos. I haven't heard yet, but it would be rather exciting if they found some Martian halos. Yeah, please.
Is there a figure for what percentage of the crystals? What percentage of the crystals would one individual observer actually see?
That's a really good question. The answer is I don't know, but I will look into it. Sure. And it's not something that I can calculate off the top of my head, but it's a very good question. So the question, if you didn't hear, was what percentage of those crystals will one particular observer see the halos essentially coming through? Yeah. No, I don't know, but I can look into it. So this looks a little bit like an alien invasion. I promise you it's not, but I'm going to leave this as a mystery and see if you can tell me at the end what this is. But I can tell you, actually, is it possible to turn this light out? Does anybody know? Is it? I don't think. No. On the wall? Ah, there we go. Is that better?
Yeah.
Oh, okay. We can start again if you want, but I'll probably just leave it there. Okay. So I can tell you that these two effects are actually the same thing. And I can tell you that they're both taken in Northern Europe. And I can also tell you that they're not the Northern Lights. They have nothing to do with the Northern Lights. Okay. So here, finally, on this section, there's another video also taken from YouTube. This was in Ecuador. Oh. There we are. Another rather beautiful display with a perhelix circle, 46-degree halo, a 22-degree halo, upper tangent arc, just to show that it's really something very, very vivid in the sky. This is not, huge enhancement of the photographs, although some of the photographs are slightly enhanced, but it really is something that you can just see with the naked eye. The easiest way to see them in general is just with a pair of sunglasses. So take a pair of sunglasses, block the sun out, and you'll be able to see these very, very clearly. So the next part of the talk is actually about, oh yes, sorry.
Why is the inside of a halo sharper than the outside?
So again, it's to do with the distribution. You can work out, if you have the crystal at a particular orientation and the light is passing through it, then you can work out, given the particular angle, what the distribution of light rays coming out will be. So you can work out the distribution for the angle, and you'll find that it's sharpest, presumably just on the inside than on the outside. So I haven't done the calculation, but you should be able to show precisely that exactly from the distribution. Yep. So I'm going to move now. We're going to do a phase transition from ice to water. And there's a lot of text here, but I just want to read a little bit from it. So this was actually from Descartes in 1637, who was the first to really understand about the nature of rainbows. And he talked in particular about caustics. So he understood caustics in terms of the way light interacted with droplets. And what he said was that caustics are the brightest places in an optical field. They are the singularities of geometric optics. The most familiar caustic is the rainbow, a grossly distorted image of the sun in the form of a giant arc in the sky space of directions, formed by the angular focusing of sunlight that has been twice refracted and once reflected in raindrops. And I think that's a rather lovely view of it, that the rainbow is a grossly distorted image of the sun. That's exactly what it is. It's the light from the sun, which has come essentially parallel to us from the sun, and then is just grossly distorted into this wonderful pattern through refraction and reflection through raindrops. So in fact, we can work out precisely what's happening to build up a rainbow by taking a droplet of water and working out, as light comes in here horizontally, in which direction it's going to come out. And actually what you find is that, again, there's a much higher distribution coming out in one particular direction. This goes rather too quickly. But the intensity of light is most extreme here. Okay? And then, in fact, on the inside, you'll see that there's still a little bit of light. And this, I think, is the answer to your question, that there's quite a sharp cutoff on this side. So the one side of the rainbow will therefore be much sharper than the other. You can work this out for the different colors, and what you find is that the maximum angle of reflection is actually different for each different color. So what you find, again, is that what you're seeing is the splitting of the colors, and you end up with a rainbow. Sometimes it's a rainbow. In fact, if you look at it at sunset or sunrise and you see a rainbow, which is when you're going to see the largest rainbows, what you can actually see sometimes is a red bow. So this top left one here is actually a double red bow taken by Steve Jurvetson. This is simply because all the light that's reaching the droplets is in the red part of the spectrum. The rest has been scattered off by so-called Rayleigh scattering. And so what you're left with is just the red part of the light, and you get a red bow. This looks like a rainbow, but in fact this is a moonbow over a waterfall. Sometimes you'll also see not quite a rainbow, but what's caused by droplets of water, and droplets of water in mist tend to be much, much smaller than raindrops. And because of this, what happens is that rather than having a very clean refraction and reflection of the light, what you get is a diffraction effect, because essentially the size of the droplets is such that the wave nature of the light is then important. And what you end up with is a much more diffuse effect, a so-called fog bow. And because of the way the light is diffracted through, it's a more diffuse effect, and so what you end up with is a white bow. So sometimes you get a red bow, sometimes you get a white bow, and sometimes you get the full spectrum of colors. There are still, again, some mysteries. So sometimes you'll even see what's called a twin bow. This is not the same as a double rainbow. So in a twin bow, what you'll actually get is a single bow which is slightly split. It's thought that this is probably caused by non-spherical water droplets. So if you have particularly turbulent conditions as the rain is coming down and the water droplets are oscillating between two different directions, so they're sort of going from like that to like that as they come down, what you'll get is different directions of the refraction and reflection, and get this split bow, the so-called twinned bow. Of course, if you're near a body of water, then you'll see not only a double rainbow, but also the effect caused by light which comes from the sun, bounces off the water into the sky, is refracted and reflected off, and then comes back to you. So sometimes you'll see bows which seem to go off at peculiar angles, and this is simply because of the way the light is already reflected off the water and has then come back. And then, of course, you'll see the reflection itself of that bow. Here we have a picture of cloud iridescence, and essentially cloud iridescence is really just part of a corona. So in newly formed clouds, the size of the droplets of water tend to be very similar. So as the cloud forms, the droplets are very similar, and again cause this diffraction effect as the light passes through. And so you get this beautiful set of colors. Here, this is a large cloud which has been there for a while, and this is a newly formed cloud, and the light passes through, is diffracted, and you see these wonderful iridescent colors. So many of you who like to hike on Table Mountain will have seen effects like this, so the so-called Glories and Heiligenschein. And the glory is an effect whereby if you're standing somewhere and the sun is behind you, the light passes by, hits droplets of water, and then is reflected back but split as it does so. In fact, it's not reflected back in the way that you would expect it to be classically. If you just do the ray diagram, so you work out the reflection and refraction of the light through the droplets, actually it doesn't come back precisely in the direction it came from. In order to work that out, you actually need to see the way the light interacts with the surface itself, so-called surface waves. And if you take into account the surface waves, then you can understand the glory. You can also often see glories if you're in a plane. Oh, I should say that understanding the glory actually isn't just a matter of understanding the way the light bends through here. In fact, one has to use a theory called Mie theory. And to do this, or Mie scattering theory, in order to do this, what you actually have to do is to look at the different modes of the light, the different the different frequencies of light, essentially, as it passes through. You have to add them up in various different ways, and then you can simulate the glory. It's actually not a very simple thing to understand. It's much, much more complicated, for instance, than the halo or the rainbow. So the glory is really a much more complicated thing to calculate exactly what's going on. Here's a picture just of a glory around the shadow of a plane on the cloud below. And the nice thing about this is that you can work out precisely where you are in the plane, because, of course, you will always be in the center of the glory. Okay? The observer will always be in the center. So in this case, I think I was ever so slightly just ahead of the left wing there. So, of course, if two people take photos of glories, what they're seeing is slightly different, because each of them will be at the center of their own glory. There's something rather poetic about that. So if you ever see the contrail shadow, so the contrail, the vapor trail left behind an aeroplane, you'll see the shadow here, and then actually it's not very easy to see here, but at the end of the contrail shadow, here you see the glory. If you look the other way, so of course this is coming from the sun, so you've got the sun here, the aeroplane here, and the glory here. If you look out the other window, sometimes, you wouldn't see it in this particular occasion, but sometimes if the conditions are right, what you'll see is a so-called sub-sun. So this is a reflection of the sun, again on plate crystals, so these are horizontal plate crystals acting like mirrors. So the cloud below you, if it's made up of ice crystals, will itself be like a reflective layer, and you can see a perfect image of the sun reflected in the cloud below. From planes, it's also a great place to see halos in general as you pass through particular conditions of the atmosphere. So here is, again, a rather nice 22-degree halo around the sun taken over a wing of an aeroplane. And depending on the size of the droplets and the particular distribution of droplets, you can get many different patterns of glory. So you can get them with multiple colors sort of resonating out from the center. Also from the air, this was a particularly rare photo. So this was actually taken over Mongolia. This was, when was it? 8 years ago now. These are noctilucent clouds, so it's already dark by this time. But because these clouds are so high, this is a high atmosphere effect. What you have is the sun below the horizon, and the light from the sun reflects and lights the clouds. So the rest of the sky is relatively dark, and you've got these beautiful wispy clouds extremely high up. So these are very, very high atmosphere effects. I seem to remember these are on the order of sort of 40 to 60 kilometers up.
Is that one spot there a moon?
That's actually Jupiter. Yeah. So I was actually trying to take a photo of Jupiter at the time, and then realized that there were these rather beautiful clouds there. A similar effect to the glory is the so-called Heiligenschein, the holy light, which comes from droplets of mist or dew on the ground on blades of grass. What's actually happening here is that the light is coming in, is being refracted through the water droplet, bounces off the blade of grass at the back, and then is reflected and refracted back through. And so what you see here, so this is a photo, this isn't mine, this was by Les Cowley. So you see there again a sort of halo, a glow around around your head. So you don't need to take a photo to see this. But if you're on somewhere on a morning where there's a lot of dew on the grass and the sun is relatively low, look at your shadow and see that around the shadow there'll be this particular sort of glow of light. Something similar happens. So this is a photo actually taken on the moon by Michael Light. And it doesn't have to be on the moon to see an effect like this, but essentially this is a so-called opposition effect, whereby the light from behind you strikes the ground, but if there are a particular distribution of gravel or soil on the ground, which itself is causing shadows, then you won't see the shadows in the region directly in front of you, because precisely they're blocked by the soil, by the rocks, by the pebbles, but you will see the shadows off to the side because you can see underneath. So essentially what you see is a lighter distribution around your head. Okay, that wasn't very clearly explained, I'm afraid. But if you're interested, if that didn't make sense and you're interested, I can explain on the board in more detail later on. But essentially, it's an effect whereby this is the region around the observer's head. So again, this is the astronaut taking a photo. The sun is behind, the light is coming past. And what you find here is that there's a region, a sort of halo, a glow effect in the region where the shadows of the rocks are themselves hidden by the rocks. Okay, I don't know if that makes sense. So of course other things can block the sun out, so often you'll get these so-called crepuscular rays, the rays of sun which appear to be sort of coming out from the sun, where in fact what you're seeing is the rest of the sky is blocked by clouds. So what you're really seeing here is shadows from the clouds, and the light coming through is the light directly from the sun. This is a rather strange effect because it looks like it's coming out in all different directions, but really, of course, these lines are parallel. So this is really a perspective effect. That the lines, the parallel lines from the sun are coming directly around you like this, and while they're parallel, the perspective makes it look like they're coming out in all different directions. So if you have the sun over here on the horizon, and you have clouds on the horizon, and the clouds are blocking the sun, then you'll see these crepuscular rays. And of course, the crepuscular rays are coming like this. And if you're lucky enough, if the crepuscular rays are very strong, what you'll actually see is that they'll come back together at the anti-solar point, the other side of the sky. So this I actually took in Musenberg a few years ago. So here you can see my shadow, and here you can just see the crepuscular rays coming back together to meet precisely at the anti-solar point, which of course is the point where my head is in the shadow. Okay? These are so-called anti-crepuscular rays, and if you're lucky, you'll actually see them going all the way across the sky, so-called sky-wide rays. So this might not be very clear here, but here you have crepuscular rays coming out from the sun here, and you can see them going all the way around and coming back together at the anti-solar point opposite the sun. So this is an image that I showed before. This I took in Korea a few years ago. So this is a cloud shadow. So essentially what you have here, you have the sun, you have a cloud, and then below the cloud you have a layer of mist. Actually, there are two layers of mist here. And what this is the shadow of the cloud itself on the two layers of mist below it. It looks rather strange. It looks like the cloud is, the shadow is actually behind the cloud, but again, that's just a perspective effect. So if you imagine you've got sun, cloud, mist, you, what you're actually going to see is the shadow of the cloud apparently around the cloud itself. So it looks like it's behind, but really the shadow itself is in front. You can see the same thing from above. Again, if you've got sort of misty conditions, then you'll see the shadow of a cloud zooming off into the distance, again, going precisely to the anti-solar point. So you can get many effects which don't necessarily come just from water. So this is a sunset effect. This was caused by a volcano. This was back in 2008. The Caustics volcano, which was in Alaska, blew huge amounts of dust and gas into the atmosphere. And for months afterwards, you'll see much more enhanced, much more vivid sunsets all around the world. So if you see reports of a large volcano, look out and see that actually the sunsets locally will be affected. So these very vivid yellows and oranges were precisely caused by the eruption at Caustics. So the last thing that I want to talk about are other sunset effects. So this is a so-called splitting of the sun, or a sunset mirage. And this is caused by a particular effect. This was taken over the ocean in France. And what you have, so normally you would expect that the temperature of the air from the ground up should get lower and lower. Okay, we know that high in the atmosphere, the temperature is very low, and down towards the ground it should be warmer and warmer. But sometimes what will happen is that because of the conditions through the day, in the evening what you'll have is that the temperature will get lower and lower, and then you'll have a layer of warmer air in the middle, and then it'll get lower again. So this is a rough graph of the altitude versus the temperature, so it'll get lower and lower, and then there'll be a part in the middle where it's higher temperature, and then it'll get lower again. And what this causes is in effect, because light is bent through different angles as it passes through different densities of the air, what you get is a sort of magnifying effect. So you can actually end up with two different images of the sun, which is precisely what's happening here. One is passing through simply the warmer air here, and one is passing almost like it's going through a lens. So this is simply another image of the sun here, as if it's passing through a lens caused by this warmer layer of air. Yeah?
This is exactly happening this time of the year along the west coast.
Exactly. So yeah, look out for this, and you will very often see this splitting of the sun. So you'll see multiple images of the sun. Yeah?
Are those two images meant to be exactly the same portion of the sun?
So in fact, it's probably the case that this image here is actually the whole sun. Okay? This clearly is just a portion of the sun. This part here is probably the whole sun, entirely distorted as it passes through that layer.
Is this what people are talking about when they're saying they've seen a UFO?
But it could be. Could well be. I mean, you see some pretty strange configurations depending. So this is a very simple one, but sometimes you'll see some very strange configurations of things above the sun. So I wouldn't be surprised if people are confused by that. So the green flash is caused by two things. It's first of all caused by this particular temperature inversion. And secondly, it's caused by the fact that the green and the red light coming from the sun are bent through slightly different angles as they come through the atmosphere. So the green light, in fact, is bent slightly less than is the red light, and what that means is that the image of the sun, if you imagine splitting the spectrum of the sun into just green and red, then the green part of the sun is actually slightly above the red part of the sun. So there's actually two images, and so what you'll see, so here you've got an image of the sun, and you'll see a green rim at the top and a red rim at the bottom. And as this part of the green rim passes through this temperature inversion, what you can have, so you can have some very, very powerful effects with the sort of magnification of that region. And so what you can have, this is a picture. So here, this is just a picture of the moon. Again, you just see a red rim at the bottom and a green rim at the top. Okay, it's not very, very strong here, but what you can have as that passes through this temperature inversion, what you can get as the green part passes through is a sudden magnification, and you end up with a green flash. Okay. It's subtle, so the green flash, if you've never seen it, really lasts a fraction of a second, maybe a second or so.
Have you ever seen
it? I've seen many, yeah. I don't know if I have any of my photos in here, probably not. So I've taken probably 5 or 6 photos of it and seen it maybe a dozen times. Sometimes from aeroplanes, sometimes over the sea. But yeah, absolutely, when you know the right conditions to look at it in, it's actually not that rare. So in fact, it seems, Henri, looking at this, that this is really just one portion of the sun which is being magnified. So I'd have to work out the exact way the light passes through the temperature inversion layer. So I guess it depends on the form of the temperature inversion as to whether you get the whole image of the sun or just a portion of it. Yeah?
But the last little bit we saw there was red, not green.
Was red. Ooh. The very top bit. Oh. I turned away. Let's see again. That's green. Yeah. So the very, very top bit as it splits off is green. Again, it depends precisely on the atmospheric conditions. So it's not as simple as simply having a single temperature inversion. Generally, you've got multiple layers. But the effect certainly of the splitting into green and red is very clear. But it just depends on that temperature inversion as to the way the flash itself occurs. In fact, sometimes you'll even see the blue part of the spectrum, which of course is scattered much more than the rest. You'll even see the blue part of the spectrum. So here, these are multiple green and blue flashes. So here you have blue flashes. I've seen the blue flash once, but it's quite a lot more rare.
Can I just ask, is
Yeah.
this anything, I mean, it's completely, stupid. But,
No worries.
you know, when you have your eyes tested in
Mhm.
optician, they
Mhm.
use a green and a red light
Sure.
and ask you which is the brightest. Is that
Okay.
anything to do with this kind of effect?
Oh gosh, that's a good question. I don't know what the reason that opticians do that,
Okay.
so I don't think I could answer that question. But certainly, I mean, so in the sense that our eyes deal with green and red light differently, that's really to do with the sensors and the photoreceptors in the eyes, rather than the different ways the light is refracted.
Okay.
So I think they're probably not related. Yeah.
Colourblindness.
Well, that's true. Yeah, so color blindness certainly in terms of the different receptors. That's yeah. Okay, so I'm going to show you a last couple of things. So here we have a video, and this video was of a rocket launch a few years ago. And there are two beautiful effects that happen here. First of all, you'll see a solar halo, and the rocket will pass by the solar halo, but as it passes through a particular layer of cloud, the shock wave from the rocket will distort the halo in a particularly special way. So you'll see the Sundog, in fact not a halo, but a Sundog, just up to the top right in just a moment. So there's the Sundog there. And as it passes through, you see the shock wave, and essentially what's happening as the shock wave passes through, you've got higher and lower regions of pressure, and as that happens, you get condensation of water passing through in this wonderful wave. And of course, as it goes past the Sundog, because of course the Sundog is made of crystals lying flat, as that happens, it rocks them, and the Sundog is destroyed. So one more time. And then finally, so this a final video. Does anybody know what this dot passing across the screen is? It's not a meteor. So this was a video taken by Kevin Fetter, again 5 or 6 years ago. So somebody was working on the outside of the International Space Station, and NASA was videoing precisely what was happening. And of course, it's relatively easy to see the International Space Station as it whizzes past. You can look online and see what's happening. But this astronaut who was working on the outside of the International Space Station had a toolbox. And he let go of the toolbox. And it went off into space, but NASA knew exactly where it was. They tracked its trajectory. And Kevin Fetter worked out where it would be in the sky. So what you're seeing here is actually the toolbox from the International Space Station as it whizzes by. So this is really a sort of philosophical note to say that if you know what you're looking for and know where to look, there's really incredible things to see out there. So I hope you enjoy.
Would the toolbox have now?
That's a very good question. I don't know. Yeah, it's a good question.
Not likely to encounter.
No, I don't think so. I think it's going to be up there for a little while to come. So, thank you very much.
Jonathan, thank you for that really interesting tour of atmospheric effects. We have time for a few questions. Are there any questions?
I have a question. Does anybody know what this is? It's not a corona.
Can you get a green flash on a rising star?
On a rising star, you would be able to. The difference is that you would be very unlikely to be able to see anything because we can't resolve the star. The position of the green and the red. Oh, actually, no, that's a good point. You wouldn't need to resolve it because you would be able to see. So it wouldn't be a flash because what you would have, I imagine, is a continuum of the spectrum from red to green. So essentially, as you see the star on the horizon, you'll see it extended, the green part of the spectrum and the red part of the spectrum. So you wouldn't see it as a flash, but you will see it as sort of smeared out in the sky. That's my guess. Yeah.
Is that light from below?
It is light from below, yes. In fact, so this is light from street lamps. So these are plate crystals, again acting as mirrors. So this is, you imagine a sky full of mirrors lying horizontally. These are the street lights reflected off the mirrors. It's the same thing as this. Yep.
Nice.
Yeah.
I was observing a very powerful mirage on Friday afternoon over on the Atlantic Atlantic coast
Mhm.
here of Cape Town. And very, very powerful mirage with, ships were looking huge.
Mhm.
Those interesting things that happened. But one thing that I noticed is that there seemed to be a lot of very bright columns of light coming up from the sea,
Mhm.
up towards the mirage, as it were. Any explanation for that?
Interesting.
I've seen it a little bit before, but not as dramatically as last Friday.
Interesting. I don't know offhand. Did you manage to get any photos of it?
Unfortunately, I never take my camera with me
Ah,
to
okay.
the beach. So
Sure. Yeah, I don't know what that would be offhand, but I can look into that.
Thank you.
Yeah.
Any last question?
I was interested in the reflection of the sun on the water, because I'm very interested in prehistory. Around the ancient stone circle monuments, they had a deep ditch called a henge, which some people think was filled with water specifically to reflect light. Now, I just wondered if you had any idea why they would want to, would it be just to avoid looking directly at the sun? Why would they want to use a ring of water?
Mhm.
For reflective purposes in terms of observing light from the sky, I think.
That's a good question. Well, I mean, one thing is that having a reflective surface means that you get more light essentially coming to one particular place. But I don't know any specific significance of that. I don't know if Henri, you might have any insight into that. No, I've never heard of that in terms of the study of atmospheric optics. I don't know if, I certainly know that the henges, the sort of stone henges, were often used presumably for astronomical purposes, but in this case I don't know what a water henge would be used for. These are all great questions that I don't know the answers to.
And we all know about the northern lights.
Yes.
Is there a similar thing in the southern?
Yeah, there absolutely is. So there are the southern lights. The difference is just that there's a lot lower population in the same region in the southern hemisphere than there is in the northern hemisphere. So in the north you have Canada and you have Norway and Sweden, and there's a much higher density of people compared to the same region in the south. So it's, as far as I know, it's simply a population effect. Yeah.
So just to ask again about the green flash.
Mhm.
My father was at sea for 20 years. He told me about it.
Mhm.
So he said, it's you've got a lovely clear horizon. You look for it over and over again, never once saw it.
Right.
I always assumed it was an optical illusion
Mhm.
inside the eye. You say it's a real thing
Yes.
in
Oh,
the
yeah.
real world.
Yep.
My impression was the whole sky gets lit up with wonderful emerald flare. You're saying it's like a little layer on top of the sun. Is that right?
Yeah, that's right. So there's a sort of mythology behind it whereby it got talked up into this huge flash, or even a column of light which came out of the sun. But unfortunately, that's not true. There are tales of sailors seeing that, but nobody has ever documented that in any scientific way. So the green flash is known about and seen fairly regularly. Really, it's a subtle effect, but a beautiful one. Yeah.
So I think with that we'll close, and I'd like to just thank you again, Dr. Schock, for
Thank you.
sharing your enthusiasm and great insight into this very interesting topic. So
Great.
thank you once again.
Thank you.